Okay, we're going to look at inclined planes and the forces acting on an object on an inclined plane. So first we're going to draw the Fn and Fg forces. So we can see that gravity is acting straight down. Fg is equal to m times g, and the normal force is acting perpendicular to the surface that you are on. We're going to mark in the direction of acceleration. Obviously, this will be accelerating down the ramp, and we show the acceleration parallel to the surface of the ramp. We're going to choose a coordinate system with x in the same direction as the acceleration. Just makes life much easier. And y obviously has to be perpendicular to the x-axis. So here we see our x direction down the ramp, parallel to acceleration, and the y is pointing perpendicular to x, which is also perpendicular to the surface of the ramp. We're going to look at a little bit of trigonometry. We've got a right angle triangle right here. Here's an angle marked theta. This angle right in here would obviously be 90 degrees minus theta. So let's say theta is 30. This is our 90. This angle right here is going to be 90 minus 30, which would be 60. We want to know the angle in here because we're going to need it in a few minutes. If this angle was 60, we have to realize that from here to here is a right angle. This is 60. The only thing that's left over is 30. Basically what we're showing is whatever angle that you're given right here, say it's 30 degrees, that's going to be the exact same angle that appears in this region right here. Now we want to take gravity and break it into its components. Why do we have to break it into components? Gravity is acting straight down, but we have a normal force acting perpendicular to the surface. If we're going down the ramp, which is this direction right here, gravity, you'll notice, is not parallel nor perpendicular to either the normal or the acceleration. So we'll have to use some components. So this component right here is Fgy, which is the y component of gravity. It's this vector right here. And apparently it's mg cosine of theta. And this vector right in here is the x component pointing down the ramp. This is Fgx, or mg sine theta. So a little bit of Newton's second law. Let's look at all the sum of the forces in the x direction. X direction, remember, is down the ramp. I've got max, which is acceleration in the x direction, or just m times a, which is Newton's second law. The only force acting down the ramp is this force right here, which is Fgx, or mg sine theta. So mg sine theta, the net force acting down the ramp, is equal to m times a. So we could calculate the acceleration due to gravity on the ramp. Sum of forces in the y direction. Well, I've got this y component of gravity, which is this green one right here, mg cosine theta, and I've also got the normal pointing up. So I've got the normal up, which is positive, and then I'm subtracting off the gravity component because it's downwards. And those two actually have to equal 0 because there is no net movement of this skier or this object down into the plane. Now the question would be, why is the x component mg sine theta, and why is the y component mg cos theta? So we've got this written down. Here's the gravity component in the y direction. Here's the gravity component in the x direction. So anytime we've done a calculation, any x component has always been a cos value, and any y component has always been a sine value. These seem to be flipped. So why is that? So if we just twist our diagram slightly, we can draw on our vectors. This is the y component. Here's the x component, and there's our gravity. Gravity now looks like it's on an angle. I'm going to slide the x component downwards, and we've now created a right angle triangle. So take our right angle triangle, and now let's fill in all of the pieces of the right angle triangle. Hypotenuse is gravity, which is just m times g. We're saying this is our x component, which is mg sine theta. and we're saying this is the y component, which is mg cos theta. If I'm given this angle right here, that's the opposite and that's the hypotenuse. And the trig ratio for opposite over hypotenuse is sine. Given this angle right here, this is the adjacent side, and that's the hypotenuse. So the ratio of adjacent to hypotenuse is cos. So it's basically some simple trigonometry. Sine is opposite over hypotenuse. Cos is adjacent over hypotenuse. So the big difference between these vector components and any ones that we've ever done before, the x component is the sine of the angle, and the y component is the cos. Now that's due to the fact that we have now made our triangle touching the y-axis as opposed to our normal diagram, which the triangle is touching the x-axis. So we need to be very careful, but there's a little explanation of why that is.